37%. P of x, probability of, that's the probability of what? Of one record hashing to a given slot. So the chance that one slot has only one record hashing to it is 37%. Another way of putting that is that 37% of the slots have one record hashing to them. Does that work for you? Better? Okay. So 37% of the slots have one record hashing to them. Under what assumption? Under the equally likely assumption. Because what we did, I know I messed this up with the messiness here, but basically what we did was we basically took, we took this right here, and the probability, remember what the probability was? The probability was we're going to hash R record, so it's going to be R over N. We took the limit of this as N went to infinity, and we came up with this probability, equally likely probability. We came up with this binomial distribution, which ended up becoming the Poisson distribution. So that means that 37% of the slots have one record hash to them. Okay, can we draw any inferences from that? If 37% of slots have one record hashing to them, what else do we know for sure? What's 1 minus 37%? 60%, go ahead.
More than all.
No, not exactly accurate, be careful. 63% of the slots have either more than one record hash to them or no records hash to them. Is that true? Has to be true. Because we know 37% have one record. That means the other ones do not have just one record hash to them. Do we know how many we expect to have two records hash to them? No. How about 3? No. How about 0? No. How about if we wanted to find 0? Let's find 0. What's the probability that a slot has no records hashed to it? That's the probability that x is equal to 0. What's R over N? 1 to the, which is?
1.
E to the minus 1 over
0 factorial.
0 factorial. What's 0 factorial?
1.
Okay, so what is P of 0? So this tells us that 37% of the slots will have one key hash to them. Let's put this into perspective. Let's create a table with 1,000 slots. How many of them will have exactly one record hash to them? 370 randomly located slots will have one record hash to them. 370 more will have 0 records hashing to them. So how much is 37% plus 37%? That's 74%. So let's make a statement. I'll start it, you'll finish it up. 70% of the slots will have say again? We'll have 0 or 1 records hashed to them. 74%. Now finish this other statement. 26% of the slots will have 2 or more. So 2 or more records hashed to them. You understand good or bad? Let me ask you a question. Let's say N is 1,000. 1,000 slots. How many slots will have no records hashed to them? Okay. Now the very difficult question follows. How many of the slots will be completely empty? No. It's a good guess, but it's not even close. how many slots will be completely empty? The answer is, who knows the answer? The correct answer is 0. Why?
5 minutes.
Because the packing density is 100%. So that means those records gotta go somewhere. Okay, so don't, I know, it's a trick question. I get it, it's not a test question, it's a question just to make sure, keep you in perspective. Because R is equal to N and the packing density is 100%, every single slot will be filled. All N slots will be filled. If N is 1,000, we will have 1,000 records. Those 370 slots that have nothing hashing to them will be filled by either linear probing, quadratic probing, or some other technique. Things get more complicated. Because, for example, suppose that I have somebody and it hashes to slot I. And that's what the first one. The first one, wherever it hashes, excellent. No collision possible because nobody's in there. Second one goes in, and let's say it goes to the same slot. Just by the probability is very low in that. We know that. It's going to be 1 in a million using the 1 over 1,000. But it can happen. Not likely, but it can. If that happens, we have to put this someplace. Let's say we put it, let's say put it right next to it, by linear probing. But at the same time, let's do the following. Let's say we do a different technique. We'll hash the first one, put it wherever it goes. The second one, if it doesn't collide, leave it. If it collides, throw it away. Or put it aside. So now what we're going to do is we're going to take all the keys and we're only going to store any key that doesn't collide. If there's a collision, we will immediately put it aside, not store it. So that means how many, using this approach, how many of the 1,000 slots will be completely empty? Now the answer is going to be 370 of them will be completely empty because nobody will ever hash them, and we're only going to store you in the slot that you hashed if nobody hashed to that location before. If somebody already did, we're going to take you aside. So the question might be, interesting to answer would be, how many of the records are we going to put aside? There's an absolutely accurate estimation of that number. But for that, we would need not only P of 0 and P of 1, we also need P of 2, P of 3, P of 4, P of 5, P of 17, if you wish. Because P of 3 means what? What does P of 3 mean? The probability that a slot will have 3 keys or 3 records hashed to it. If that probability is 5%, that means out of 1,000 slots, 50 of those slots will be targeted by 3 keys. And 50 of them will go into those slots. And 100 more will be set aside. Does that make sense? The first 50. So basically, does that make sense? I don't think it makes sense to me either. So if there's a 5% chance that a slot will have 3 records hashed to it, 5%, then out of 1,000 slots, 5% will be 50 slots. So that means 50 slots someplace across this hash table. Those 50 slots, when we hash all the records through the hashing function, those 50 slots will have 1, 2, 3 records trying to get to the same slot at different times. So 50 slots will have 3 records that want to go there. So if we're going to store only non-colliding records, then when we hash the first one, it's going to go into that slot. Eventually, we'll get to another record which hashes to the same one, we'll set it aside. But we know we expect to have another record hashed to it by the Poisson distribution. So therefore, we can expect 2 records for this slot to be set aside. But since there are 50 of such slots, with a probability of 5 times 1,000 being 50, then we expect to have those 2 records for each of the 50 slots, making 100 records being set aside. If the probability of 4 records, probability x is equal to 4, is equal to 3%, then how many slots would be targeted by 4 records? 30. So 30 records would be stored successfully, and then 30 times 3, 90, would be rejected because they would be colliding. Because now you'd have the first one is okay, but the next 3 would be rejected. Does that make sense? Okay. Kind of. So let's go through this mess. This is so nice, but I can't, there's no way I'm going to go through this because it's just very messy. Okay. I'm basically just showing you how you convert the discrete binomial, the binomial probability distribution. The binomial distribution, which is this one right here, this is the binomial. When you convert it using the set of assumptions where the probabilities are over n, and you take the limit as n goes to infinity, ends up being the Poisson distribution probability, which is awesome. Now, so now what I have is I have the result of the Poisson as we just did it. Remember we get the 36.8%? Well, that's the number we had for P1 and P0 when R over N, which is also known as the packing density, was 100%. By the way, in standard hashing, we cannot have R more than N, because if we do, then we can't store 100% of our data. So packing density maxes out at 100. You can't go over 100, but you can go under. So notice, so these are the probabilities. Notice that they are starting to approximate. Notice that I stopped at P0, P1, 2, 3, 4, 5. I didn't go to P6, P7, P8. If I added those in, this would start getting closer and closer to 1. Because the probability that some number of records will hash to you has to equal to 100%. Because some number of records have to hash to you. So you try all the possible numbers. Of course, as the value of x is increasing, this is going less and less and less. So you can see that in each case, because r over n is equal to 1, then we have r over n, which is the probability, to the power of x times e to the minus probability over x factorial. And we continue that as x is 5 factorial, but this is simply going to just stay at 1. We can use our probability function p of x to predict the number of hash table slots with 1, 2, 3, 4, etc. These hashing to it given by npx. For example, if the probability that a given slot will have only one key hash to it is 36.8, then with 500 slots, 184 slots will have one key hash to it. Makes sense. Makes sense. Now, let's look at an example where we have a concrete number. So let's say R is 5,000 records and N is 5,000 slots. So our packing density is 100%. That means we're following our probabilities from this page. So we're going to say N times the probability of 0. So N is the total number of slots times the probability of 0. That gives me 1840. What does that mean? What's 1,840? That's the number of what? Slots where 0 records would target them. Now, this sounds, I would say, outrageously crazy. Because we developed this model using the binomial distribution with a 1 over n likely probability. And I'm telling you right now that 1,840 slots will have 0 records hashing to them using the best possible hashing function we can provide. It's absolutely true, but it does sound outrageous. 1,840 of those 5,000 slots will have exactly one record hash to them. There's going to be 920 slots that will have two records going to them, 305 with 3, 75 with 4. There'll be 15 slots with 5. I don't know, maybe 2 or 3 with 6, maybe 0.8 with 7, very diminishing. So the question is, what can we do to improve what we see as a potential problem? And I guess what we can do is we can try to lower the packing density. And if we lower the packing density, R over N goes to less than 1. For example, R could be equal to 600 or 6,000, and then it could be 8,000, then we have 0.75. What happens in that case? Well, what happens in that case is that we have 0.75 and negative 0.75. Everything else stays the same. So in our example here, we're going to reduce the probability. We're going to reduce the probability to 40%, which is a very unrealistic reduction because it's extremely wasteful of memory. Your packing density is 40%. That means 60% of your space will never be used because only 40% is needed. It will have a very low collision count relative to what we had before. You can see that our probability is 0.4. So it's 0.4 to x times e to the minus 0.4 divided by x factorial. And in this case, let's see what we have here. This tells us that 67% of the slots will have 0 records hash to them, which sounds even more outrageous than before, but it shouldn't be, because with 40% packing density, 60% of the slots won't even get used at all. So 67 not being targeted, that is not as alarming, because we only expected to use 60% of the space, 40% of the space anyway. 26.8% will have one record exactly hashing to the slots. 5% will have 2. 0.7% will have 3. 0.07% will have 4, and 0.006% will have 5. Let's think about this for a second. If we had 1,000 slots, if n was 1,000, what's R? It would have to be 400. So we'd have to have 400 over 1,000. Or if n was 1 billion, then R would have to be 400 million over 1 billion. It gives you the same ratio, it gives you the same probability. So we keep it with a smaller number, but we'll certainly scale up the numbers if we want to. So R over n is 4. So let's say we have 1,000, n is 1,000. Let's analyze this for a little bit. So how many of the slots are expecting no collisions, no records at all? 670 out of 1,000. 268 slots are expecting one record. How many records are there total? 400. So 268 of them will sort of go in without any conflict. Kind of, more or less. Because we don't know we don't know the sequence of their. If we could just pick and choose the right ones, we can get the right sequence, but can't have that either. How many of these slots do we have? 53. So 53 slots will take 2 records hashing to them. So how many colliding records do we expect? How many colliding records do we expect based upon P2? How many? Yes. Does everybody understand that? Yes, you understand that? Okay, so let's write this down, if I can open my bag here. Okay, opening all the wrong packets. Okay, so what we're going to do, we're going to have 53. Can you read that? Okay.
5 points.
Yeah. Huh?
That's 5 points.
Yeah, so if n is 1,000, if n is 1,000, then there are 53 slots which will have 2 records hashed to them. So that means 53 will go in, and 53 will not be able to go in. So those 53 will be colliding records. So if we go to P3, how many slots like that do we have out of 1,000? 7. How many records will go in?
7.
How many records will not go in?
14.
2 times, right? It will be 14. Let's go to the next one. So we have P of 4. How many slots do we have? Less than 1. 7 times, let's count it as 1. Let's count it as 1 and finish, and that'll give us a nice rounding. So we're going to say this is counted as 1 slot. So how many records will go in? 1. And how many will collide? 3. Okay, let's add this up together. So we have 60, 70. So 70. And that is really 70 divided by the total number of records, which is what? 400, yeah. So 70 out of 400. Well, actually, it's pretty easy to do. That's going to be 35, half of 35, 17, 17.5. So that tells us that 17.5% of the, we expect 17.5% of the records to collide. And now let's get a better answer. We expect at least 17.5 of the records to collide. It cannot be less, right? Can it be less? No, it cannot be. There's no way it can be less. There's no way it could be less. Could it be more?
Yes.
Well, let me think for a second. Maybe it could be less. I think it could be less. Yes, it could be less. Tell me how it could be less. It could be less. Well, let's take a look at this guy right here. We expect to have, on the here, we expect to have 53 records go in and 53 records get rejected. I guess it can be less. I thought I could. For a second, I didn't think a look. Let me think for a second what I was thinking. I don't think we can reduce it. So I don't think it can be less. But it can be more. How can it be more? Okay, anybody? What are these records again here? These are colliding records. Guaranteed colliding records, right? Where are they going to go? They're going to get resolved into the table somewhere. Where? If they go into one of the slots that are not targeted, that's good, which is don't know what those slots are. If they go into a slot that's going to be targeted but hasn't yet been targeted, then what happens? For example, let's say one of those records from here goes into here and becomes the first record at this one slot. Then what happens? The number of collisions increases to 4. So anytime they go someplace else, they could potentially increase the number of collisions. But this is a pretty good estimate of what we expect. Now this is still an amazing result. Because I think we said this was something like around 17.5%, right? 17.5%, if we're accurate here. And we are. That we're going to expect that many records to collide with the best possible hashing function with a ridiculously low accuracy. And I say ridiculously low because we're wasting 60% of space. If we have so let me ask you the reverse question. This is all very easy math, but you have to know how to do it. Let's say we have 1 million records. I want 1 million records with a packing density of 40%. How big is my table going to be? 1 million records with a packing density of 40%.
400,000.
Are you going the wrong way? So the question is, 1 million is 40% of what? So 0.4x is equal to 1 million. So x is going to equal to 1 million divided by 0.4. Divided by 0.4 is like multiplying it by 5 over 2. 4 over 10, 2 over 5, 5 over 2. 5 over 2 is what? 2.5. So the table would have to be 2.5 million. So a megabyte, you need 2.5 megabytes. A gigabyte, you need 2.5 gigabytes. A terabyte, you need 2.5 terabytes to get that density. Nobody's going to do that. So that's what I'm saying, it's a ridiculously low packet density. And yet, we still get 17.5% packet collisions. So what is our observation? Our observation is we're going to have collisions. We have to deal with the collisions. So there are ways of dealing with collisions that I haven't resolved fully. One of them, and I love this approach, is, and we talked about it already so you have a full understanding of it, is called chaining. So when I go to chaining, I'm going to go right back to this one right here. Because what I'm going to say is I'm going to have n records, and I'm going to have n chains. Well, chains are the same as slots. Instead of just having one in a slot, we have a single chain. So now, if we translate our Poisson probability results to a chaining example, and let's say we have 1,000 chains and 1,000 records, how many of the chains will have 0 records in the chain? It's not a trick question. Finally, you have the right answer. Okay. So 368 of the chains will be completely empty. Why? Because nobody will target them. And there's no linear probing or quadratic probing or anything like that. So 368 of the chains are going to be completely empty. So the question is, and I wanted to ask you that question first, so then I can ask you the next question: what is the length of the average chain? I don't want an answer. I want a formula. What is the length of the average chain? Well, the average chain is going to be how many? I said I had 1,000 records, right? So it's going to be 1,000 divided by 1,000 minus 368. Because I'll take the full number of records, which is going to be 1,000, and divide it by all of the chains that have something in them. So if I do hit a chain, the average chain that exists has 1,000 divided by, let's call it 632. That's 1,000 minus 368, 632. So if I'm searching for something that's in a table, what's my average number of comparisons? 1,000 divided by 632. That's the length of the average chain. Does that make sense? Assuming that all the chains are, we're dividing all the records in all chains. So what is the expected number of comparisons in a successful search? 1,000 divided by 632. what is the number of comparisons in a failed search? Different problem. Failed search. Because now failure could end up in an empty chain or non-empty chain. What's the probability that we select one of the empty chains? One out of 1,000. Yeah, one of them, but you're right. What's the probability that we select an empty chain? 36, 37%, yes. But I was thinking, what's the probability we select an empty chain? This empty chain. That's going to be 1 out of 1,000. Every chain has an equal likelihood chance of being chosen, right? Selected. So the average number of comparisons for a failed search is going to be 37% of the time, the number of comparisons will be 0. And 63% of the time, the number of comparisons will be 1,000 divided by 632. So we'll have to weigh it. So it'll be 37% times 0 plus 1 minus 37% times 1,000 divided by 632. Does that make sense? So I think chaining is a really nice way to look at this packing density of 100% because you'd never in a million years. By the way, let's just compare the number of colliding records we expect here versus here. I think this was a comparison for n equal to 1,000, am I correct? I think we did that. So this is going to be packing density was 40%. So in this one, okay, so let's look at the colliding record. So look at P2. P2 is the first expected colliding record. How many slots are here? 184. How many will collide? 184. The next one we have 61 slots with 3. So that's going to be 1 goes in, 2 goes. So it's going to be 122. Yeah. Except that it's not a fair comparison. I have to stop. It's not a fair comparison. The reason not a fair comparison is because this is 40%. What is R equal to here? R equal to 400. What's R equal to here? Okay. This was not a fair comparison. So, so we would have to compare this one with R is equal to 1,000 and N is equal to 2,500. That make sense? Because that